Welcome to the interrupts of the HT8 MCU basic tutorial. This chapter will take you to understand the interrupt functions of the HT8 MCU from 7 aspects, which are interrupt introduction, interrupt source, interrupt mechanism, interrupt wake up, interrupt service routine writing specifications, interrupt applications, and interrupt considerations. Interrupt introduction. The origin of the interrupts can be traced back to the early development of MCU systems. In the early MCUs, the CPU usually used a polling method to interact with the devices. This polling method can be likened to the job of a company's receptionist, whose task is to answer calls and transfer them to the appropriate department. Imagine being the receptionist and constantly checking your phone to see if a call is coming in. If no calls come in, you just keep waiting. If a call happens to come in, you pick it up and transfer it to the appropriate department. This active query method wastes valuable computing resources of the CPU. To improve CPU utilization, the researchers added an interrupt mechanism. An interrupt is like a phone with a ringing function. When there is no call, you can do other things. When the phone rings, you immediately drop what you are doing and answer the call. Interrupts not only service external events in real time, but also avoid wasting CPU resources. So, what is an interrupt? Let's start with an example when we are watching TV, and a call is coming in. We answer the call first. After answering, continue watching TV. Similarly, when the CPU is executing the main program, and an interrupt request comes, the CPU will first process the interrupt service routine, and then continue executing the main program after the execution is completed. So let's move on and talk about what is an interrupt. When an external event or an MCU internal function needs urgent processing, the CPU will suspend the execution of the current program and switch to execute the prearranged program for the occurrence of the event, which is known as an interrupt. Interrupt source. In the HT8 MCUs, interrupts can originate both externally and internally from the microcontrollers. The external interrupts are generated by signal transitions on the external pins, such as INT0, INT1, and so on. While the internal interrupts are generated by the interrupt requests from various MCU internal functions, such as the timer module, time bases, comparator, and so on. Interrupt mechanism. Let's learn about the parts of an interrupt. First, the interrupt source is the source that generates the interrupt and sends an interrupt request to the CPU when it needs the CPU service. In order to identify and service different interrupt requests, the interrupt source has its own interrupt request flag. When the interrupt source sends an interrupt request, the corresponding flag will be set to 1. At the same time, the interrupt source has its own little switch, that is, the interrupt enable bit, which can determine whether to allow the interrupt to be triggered. There are multiple interrupt sources in the entire interrupt system. Therefore, there is also a master switch, that is, the global interrupt enable bit, EMI, which globally enables or disables the MCU interrupt function. Finally, there is an interrupt vector, which is the entry address of the interrupt service routine, ISR. The above are the parts of an independent interrupt. In the HT8 MCUs, interrupts can be divided into independent interrupts and multifunction interrupts, where multifunction interrupts are also known as shared vector interrupts. For the independent interrupts, an interrupt source exclusively occupies an interrupt vector, while the multifunction interrupts consist of several interrupt sources and share the same interrupt vector. Similarly, these interrupt sources have their corresponding request flags and enable bits. There is also a multifunction request flag, which is set to 1 whenever one of the interrupt sources in a multifunction interrupt is triggered. At the same time, there is a multifunction enable bit, which is like the master switch of the multifunction interrupt family, controlling whether the multifunction interrupt can be triggered. In addition, the multifunction interrupts are also controlled by the global interrupt enable bit (EMI). It should be noted that the interrupt source request flags for independent interrupts and multifunction request flags for multifunction interrupts are automatically cleared when entering the interrupt service routine. The interrupt source request flags for multifunction interrupts should be cleared by users. Next, let's take a look at how interrupts operate. Take an independent interrupt as an example. First, we need to enable both the corresponding interrupt source enable bit and the global interrupt enable bit. Assuming the CPU is executing the main program, and the program counter points to the address of the next instruction to be executed. At this time, an interrupt request is generated, and the corresponding interrupt request flag is set to 1. Next, the CPU suspends the execution of the main program. In order to save the current program execution location, it is necessary to save the value of the program counter to the stack. The stack is a special part of the memory which is used to save the contents of the program counter only. Then, the CPU loads the corresponding interrupt vector address into the program counter and jumps to the interrupt service routine. At this point, in order to prevent the execution of the interrupt service routine from being interrupted by other interrupt requests, the global interrupt EMI is automatically disconnected by the MCU. Next, the CPU starts to execute the interrupt service routine. After entering the interrupt service routine, the interrupt request flag will be automatically cleared to 0. When the interrupt service routine execution is completed, the contents of the program counter will be restored from the stack. The CPU continues to execute the original program. At this point, the global interrupt EMI is automatically switched on by the MCU. The above is the operating process of an independent interrupt. So how do we know which are independent interrupts and which are multifunction interrupts? This requires to refer to the corresponding datasheet. This is the HT8 interrupt mechanism, consisting of a series of interrupts ordered by interrupt vectors. As seen from the figure, this part is the independent interrupt type. This part is the multifunction interrupt type. When multiple interrupts occur at the same time, we need to use the interrupt priority to process. The less the address value of the interrupt vector, the higher the priority of the corresponding interrupt. Interrupt wake-up. What is an interrupt wake-up? In the idle or sleep mode, the MCU will be woken up when the interrupt request flag is changed from 0 to 1. After the MCU is woken up, there are 3 common possible situations may occur. If the related interrupt is disabled, the program will resume execution at the instruction following the halt instruction. If the related interrupt is enabled but the stack is full, the program will resume execution at the instruction following the halt instruction, and the interrupt will not be immediately serviced, but will rather be serviced later when a stack level becomes free. If the related interrupt is enabled and the stack is not full, the regular interrupt response takes place. Sometimes, spurious wake-up situations may occur. For some reason, the interrupt request flag is incorrectly set to 1, resulting in a spurious wake-up. For example, noise interference on an external interrupt pin may cause the corresponding interrupt request flag to be set to 1, resulting in the generation of a spurious wake-up. What are the consequences of spurious wake-up? It causes the CPU to wake up and exit the idle or sleep mode, which increases power consumption. It results in incorrect execution of the interrupt service routine, which will affect the implementation of product functions. So how do we avoid spurious wake-up? First, troubleshoot the cause of the spurious wake-up and try to resolve it. Second, before the MCU enters the idle or sleep mode, we can set the request flags of the unwanted interrupts to 1 to disable the wake-up function. Interrupt Service Routine (ISR) Writing Specifications. Next, we'll explore the specifications for writing an Interrupt Service Routine (ISR). Note that when creating a new project in the HT8 3000, the corresponding compilation tool is selected depending on the MCU. Different compilation tools have different writing specifications. Take the HT66F3195 as an example. This device supports the Holtec compiler version 3 assembler. First, the compiler's interrupt service routine returns no data, and it cannot accept any parameters. Then fill in the corresponding interrupt address and custom interrupt service routine name. For more details, visit the Help menu of the HT8 3000 and consult the corresponding user guide. Let's take a look at an example of an independent interrupt routine. Take the external interrupt INT0 of the HT66F3195 as an example. Define the interrupt service routine name. Use the lookup table to obtain the interrupt address. The following example shows an independent interrupt corresponds to a unique interrupt event. The interrupt event can be processed once the interrupt is entered. Let's take a look at another example of a multifunction interrupt routine. Take the timer module STMP and STMA interrupt events of the HT66F3195 as an example. Define the interrupt service routine name. Use the lookup table to obtain the interrupt address. The multifunction interrupt routine includes several interrupt events. It is necessary to identify the corresponding interrupt request flag using the program, and then service and process the corresponding interrupt event. At the same time, these flags require to be manually cleared by software. Interrupt applications. How to use interrupts to implement LED blinking. We can select an independent time-based interrupt to implement LED blinking. Let's first understand the role of a time base, which is a timer that generates an interrupt request at a fixed time period. The HT66F3195 provides two time bases, namely time base 0 and time base 1, which have the same function. Next, we use the time base 0 interrupt to implement the green LED blinking. First, set the period of time base 0 to 0.512 seconds, that is, an interrupt request is generated every 0.512 seconds. Then, set the interrupt service routine to toggle the I/O level of the LED, and the execution content of each interrupt is to change the status of the light. The time to complete a blinking is 1.024 seconds. First, we need to check the interrupt vector table of the datasheet to find the time base 0 interrupt related content. Next, we begin to write the main program and interrupt service routine. In the main program, set the I/O port of the LED as an output. Configure the time base period to 0.512 seconds. Enable time base 0. The relevant configuration of the time bases will be introduced in detail in the subsequent course. Enable the time base 0 interrupt function. And enable the global interrupt. According to the solution, edit the main loop program. Before writing the interrupt service routine, we first define the interrupt service routine name and find the corresponding time base 0 interrupt address. Then, in the interrupt service routine, the blinking effect of the LED is realized by toggling the I/O level of the LED. When the MCU is running, time base 0 triggers an interrupt every 0.512 seconds, and the MCU jumps to the interrupt service routine to change the status of the LED. When the interrupt is completed, the MCU returns to the main program to continue execution. Then repeat to implement the LED blinking effect. Interrupt considerations. Let's first understand, what is interrupt nesting? Interrupt nesting means that during the execution of an interrupt service routine, a higher priority interrupt is allowed to interrupt the currently executing interrupt. After the execution of the higher priority interrupt is completed, return to the original interrupt to continue execution. However, the MCU internal hardware circuit inhibits the interrupt nesting function. When an MCU interrupt is in progress, its internal hardware circuit will automatically inhibit the interrupt nesting, that is, disable, turn off, the master switch EMI to block other interrupts. Other interrupt requests are recorded but not serviced. Only after the current interrupt processing is completed will the hardware enable the master switch EMI, causing the system to accept the interrupt request again. However, by using software programming, we can implement the interrupt nesting function. Interrupt nesting can be allowed simply by enabling the master switch EMI immediately after entering the interrupt subroutine. However, it should be noted that when the stack space is full, the interrupt request is recorded but not serviced until the stack space is free. Therefore, in situations where immediate service is required, it is important to ensure that the stack space is sufficient. In addition, in order to improve the response speed and stability of the system, the interrupt service routine should be as short and efficient as possible to avoid excessive impact on other tasks. At the same time, the interrupt service routine returns no data and does not accept any incoming parameters. If data needs to be processed, it should be implemented using global variables. However, be careful not to affect other functions that use the same global variable. The interrupt service routine and the main loop program cannot call the same function at the same time. Course summary. In this course, we have learned about interrupt function, source, mechanism, wake up, interrupt service routine writing specifications, and considerations. Through the study of this course, you will have a certain understanding of the HT8 MCU interrupt. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.